data from different instruments and calibrate them so that there's an increased accuracy and increased range that we can look at. And on top of that, to make accessible maps that are that represent that comparison using a program called QGIS in order to make the maps, the data easier to understand. So here are a few of the acronyms that were just on the screen. We've got ICESaT, GLASS, ASTRO DEM, and QGIS. And before we go into exactly how we went about comparing the data, we're going to explain what all of these are and what they do and what they mean. So ICESaT stands for Ice, Cloud, and Land Elevation Satellite, and it is it's a satellite sponsored by NASA, and it records changes in surface elevation, ice depth, cloud and aerosol heights, vegetation information, and land topography. We're specifically using it to look at the elevation of ice sheets in Greenland, as I mentioned before. And the unique thing about ICESaT is that it only has one instrument, which is GLASS, and that is what records all of these data.
Okay, so GLASS stands for the Geoscience Laser Altimeter System, and it has a laser frequency of 40 hertz, which means it shoots 40 lasers a second. Sounds like a lot, but when the satellite itself is going extremely fast, it's spread out over a large area. So how the laser measures data, it sends down a laser, and it records the time it takes for that laser to bounce down, reflect off the Earth, or the ice sheets of the ocean, or the vegetation, and for the time it takes to get back into the satellite. And with that, it can record the surface's elevation. It has an accuracy of about 15 centimeters and a precision of about 3 centimeters. So in this diagram, we have ICESaT over here, and it's showing that it's using the glass altimeter system to shoot down a laser, and the laser beam spreads out over the ground track, and it's just showing that it bounces off different surfaces such as the ocean, vegetation, and cloud cover, and the ice sheets.
And another notable thing about this is that since it is 40 lasers per second, although that seems like a lot, since the satellite is moving really fast and it's very far away, that leaves considerable gaps. That'll be important later.
So another acronym that we mentioned was ASTER, and ASTER stands for Advanced Spaceborne Thermal Emission and Reflection Radiometer. And this was a cooperative effort between NASA and the Japanese space systems, and right now it's on board Terra. And it averages about 8 minutes of data per orbit, and this data is used to create detailed maps, and these maps can be illustrate surface temperature, snow and ice extent, changes in cloud coverage, and in this project we're mainly focusing on elevation, and these elevation maps are called DEMs. So DEM stands for Digital Elevation Map, and this model is generated by using stereo pair images, and it's really similar to how our eyes perceive depth. So basically a camera takes a picture of the target at 2 different angles and then combines these 2 images into one, and this one image displays 3D terrain. And this DM is a type of raster data, and raster data contains a matrix of pixels, and each of those pixels contain a value that represents that the condition of that area. And this is as opposed to vector data, which is the GLASS data, and vector data is just a set of data points. And another satellite that uses DEMs or creates DEMs is the Worldview satellite and sensor. So the Worldview satellite is actually a commercial satellite, but recently it's paired up with the National Science Foundation to do scientific research. And so it is tasked to collect stereo pair images as well. And these images create very high resolution DEMs. They have a resolution of 2 meters.
So a program that we used for mapping a lot of our data was called QGIS, which stands for Quantum Geographical Informational System. QGIS allows us to create a map using a bunch of different data from from vector points and raster images. So rasters are basically pictures and vectors are basically points on the graph. The glass measurement system, it records its data in vectors, so it only records points. And Worldview and Astro records their images in rasters. So when we pair the two together, we can see a nice comparison of elevation. So the glass files that ICESaT was recording looks like this, a bunch of numbers, but when we put it into QGIS, it comes out to something like this. It comes with all these big X lines. And what this graph is showing us is, right here, this is basically inland Greenland, this is the coast of Greenland. The red area shows the most increase, or the largest change in elevation, which means loss of ice, and even inwards of Greenland right here, there's actually some gain in elevation, so it snowed more, it gained some ice, but we are losing a lot more ice than we are gaining. And back down here, these pictures, these are raster images from Worldview. These are DEMs.
So QGIS is just a really nice way to visualize the annoying, hard to understand, super long text files into something nice and neat like this with an actual map of the area that you're looking at.
So what was our group looking at? We were most specifically looking at outlet glaciers because that has the greatest change of elevation right now. Specifically on the Nussuaq Peninsula and the Umnak Fjords. We compared the DEMs to the glass data by layering the glass data on top of the raster images of the DEMs, and this made it easier to understand back in this image. Our goal was to find the error in the DEM because the DEM is less accurate to glass. We were assuming glass is near perfect; it's down to a couple centimeters, so we were comparing the DEMs to the actual elevation, or we were using glass to compare the DEMs to their actual elevation.
So we narrowed, first we looked at all the different laser campaigns that were spread across the entirety of Greenland, and then we narrowed down the glass data to only include our area of interest. And then we used Python to set parameters in order to do this. Then we found relevant Aster and Worldview DEMs from Reverb, and we only used those with limited cloud cover so we could see the terrain. And then we compared the glass elevations to the DEM elevations over bedrock only. This is because the glass elevations are data from 2003 to 2008, while the DEM elevations are from 1985. And this time gap that exists means that we have to make sure we focus on an area where rapidly changing elevation does not occur. So therefore, we avoid the ice and we focus on bedrock. And as you can see, the red elevation changes are shown only over bedrock, and they completely avoid the ice.
Okay, so when we started, we set out a plan to say, hey, how are we going to get this all done? So we start off by reading in the elevations from the glass files, and we are pulling out specifically the longitude, latitude, and elevation so we can find those specific spots. And